Solutions of an ODE. Suppose that phi is a real valued function defined on an interval I, phi prime, phi double prime, and its nth derivative exist and continuous on that interval I, and f of t, comma phi of t, comma phi prime of t, comma phi to the nth derivative at t equals 0 for all t in that interval, then the function y equals phi of t is said to be a solution of the equation on that interval I. For example, let's have a function phi of t equals t squared. This is a solution of the ordinary differential equation y prime equals 2t on the interval negative infinity to positive infinity, because phi is a real valued function defined on an interval. Both phi and phi prime exist and continuous on the interval, and phi prime of t equals 2t. If we substitute phi prime in the equation here, we get 2t equals 2t, which is true for all value of t in that interval. Hence, by definition, phi of t equals t squared is a solution of this differential equation. Y prime equals 2t. Similarly, phi of t defined by 1 over 1 minus t is a solution of this differential equation. Y prime equals y squared on the open interval 1 to positive infinity. Let's see a non-example. Let's have a function phi of t equals e to the t plus 2. This is not a solution of the equation y prime equals y, because even though the first two conditions are met, namely phi is a real valued function and both phi and its first derivative phi prime exist, however, the third condition is not satisfied. Phi prime, which is equals to e to the t, which is not equal to phi of t, because if we substitute the value of phi and its first derivative into the equation, for no value of t, the equation is true. Hence, this function is not a solution of this differential equation. If we plot the graph of a solution of an ODE, we get a solution curve, also known as the integral curve. Consider the following ODE. Y prime equals negative y squared, and a function phi, which is a real valued function defined by this phi of t equals 1 over t. We note this, that phi is continuous and differentiable on its domain of definition. However, phi is not a solution on its domain of definition, but it is a solution on the intervals from 0 to plus infinity or negative infinity to 0. This is the difference between a function and a solution of an ODE. Note that a solution must be defined on an interval. So the domain of definition of a function may not be an interval. For that reason, a function may not be a solution of an ODE. Let's see the figure below. Here you see phi of t defined for all value of t except possibly at 0. And phi of t equals 1 over t defined for the positive values of t. So this blue curve is a solution of the differential equation. we stated earlier, y prime equals negative y squared. So this equation, this graph is a solution curve of the differential equation y prime equals negative y squared. This is not a solution of that differential equation. Types of solution. If an ODE has a solution of this form, where the dependent variable is explicitly expressed as a function of the independent variable, then it is called an explicit solution of the ordinary differential equation. For example, phi of t equals t squared plus 1 is an explicit solution of the ordinary differential equation y prime equals 2t on the interval negative infinity to positive infinity. A relation, some function of x and y equals 0, is said to be an implicit solution of the ordinary differential equation on an interval I if there exists one function phi that satisfies the relation as well as the ordinary differential equation. So we are talking about a function which satisfies this relation and the ordinary differential equation as well. Let's see an example. X squared plus y squared equals 1. This defines two functions, phi 1 and phi 2, on the interval negative 1 to 1. Both are real valued functions. So this function, phi 1, defined by the positive square root of 1 minus x squared, is a solution of the differential equation y times y prime plus x equals 0. Please verify. Similarly, phi 2, defined by negative square root of the 1 minus x squared, is another solution of the same differential equation. Let's have a look at the graphs of the solution. So this is phi 1, defined over the interval negative 1 to 1. And this is phi 2, also defined over the interval negative 1 to 1, are both solutions of the differential equation y times y prime plus x equals 0. However, the equation x squared plus y squared equals 0 doesn't describe the solution of the differential equation. Notice this is not a function. Family of solutions. Let's consider an ODE y prime equals y. We can show that for any arbitrary constant c, the function defined here satisfies the ordinary differential equation for all t in the interval negative infinity to positive infinity. For each value of the constant c, phi defines a solution. Let's see some of the solution curves in the following figure. So if we set the value of c, for example, negative 2, so we obtain this solution. If we set the value of c as negative 1, we get this solution. If we set the value of c equals 0, we get this solution, the red, which is the x-axis. If we set the value of c equals 1, we get the blue solution. And similarly, if we set the value of c as 2, we get this solution. C doesn't need to be necessarily integers. It can be any real number. We have an infinite family of solution. These are few members of that family.